Welcome to our software news webinar. My name is Christian Schulze and I'm the head of software development. I will lead you through today's webinar. This is our agenda for today. We will give you an update on recent developments in our software portfolio, including important changes and new features. I will start with a brief introduction. Then Ingo will take over with a 10 minutes update on TIL. Andreas will follow with a 10 minutes overview of the TIL Add-On Battery. After that, Mario will present the latest updates to Dave, our data visualization environment. Next, Philip will walk us through the last two releases of MoBA Automation, or maybe even three. We'll conclude with a Q&A session. Please post your questions in the chat. Maybe we can answer them directly. Maybe we can answer them at the end of each presentation. But if we are behind schedule, we will answer them in the end at the Q&A session. So let's start with a review. I want to mention three conferences we attended. First, we started with a high temperature heat pump symposium 2026. That is a high temperature heat pump technologies driving industrial decarbonization conference. So if you're in contact with this, this would be interesting for you. And the ZBT Hydrogen Days. This conference gives you direct access to current hydrogen innovations. And of course, the DKV meeting in Magdeburg, a concentrated overview of the latest trends and regulatory developments in refrigeration and air conditioning and heat pump technologies. Then I want to mention our research activities for the next years. So we started new research projects. I just want to mention the topics, and you can see the partners which are also joining the projects. So we are working on fuel cells and aviation. So we have models for that. We are working on direct air capture. So collecting CO2 from the air and store it in some way. We are working on rapid development process of safe batteries. So there's also a connection to the add-on battery we will speak about later. And vanadium redox flow batteries. Okay, and I want to mention our new reseller. Trident Infosol is a new reseller in India. So if you're in need of technical support, you can get in touch with them, and you can also purchase our software from them. Usually we cannot speak too much about what we are working on. So I'm glad that Everlance, formerly MAN Energy Solutions, published some details about the projects we have been working on and is fine with us presenting what we have contributed to. So there are the three heat pumps you can see there on the list. We have also a LinkedIn post about it. We supported them in the model development, parameterization, and calibration. We simulated startup phases, switching conditions, and overall operation. And we worked on the analysis and optimization of operation control concepts, including critical trip scenarios. There's also a connection to the shell and tube heat exchangers you will see later. Okay, so there are also some upcoming events. The Modelica in Process Engineering meeting, which is organized by TLK Energy. It focuses on process engineering, but also on electrochemistry, which we are working on. So direct air capture, electrolyzers, and fuel cells. And there's the CATIA User Symposium we will attend, the Modelica conference in Asia, and of course, the Thermosim conference, which is organized by TLK-Thermo, TLK Energy, LTX, and XRG. And I want to invite you, if you're in Germany and you want to learn something or to contribute on thermal system simulation, you're invited. So you can use the QR code or just Google the name, you'll find it. And we will attend the Chillventer. Okay, I want to mention again our training courses, so you can see them on our website. There are 3 in-person trainings in June, in September and December planned. If you need some in-house courses, just get in contact with us. We are also preparing more advanced trainings, which are split in smaller modules, and they are going to be published during the year. So if you needs of specific training material, just get in touch with us. You can follow us on LinkedIn. Some of the things I just mentioned are also published on our LinkedIn channel, and we also have a YouTube channel. So we provide some smaller tutorial videos, for instance, about our data map creator. And yeah, if you are interested in these updates, just follow us. Okay, so let's get back to our agenda, and I want to hand over to Ingo.
Yes, thank you, Christian, for the introduction. I will start my presentation and sharing the screen. Okay, and now I will give a few informations, a selection of new components in the TIL and TILMedia suite and the release 2026.1. Yeah, my name is Ingo Frohböse. I'm a developer, a user of this software, and also first contact person for you. So this is a selection I want to present today. We have the news in the shell and tube heat exchangers, which are typically used in industrial plants, as already mentioned, with Everlands together, for example. Then we have a new compressor model with vapor injection. I want to go into a few details. Then I show the unified splitter models for all fluid types in TIL TILMedia. Then a few improvements of the TILMedia calculation routines. And finally, I'm showing a data center cooling system, which is new as a TIL example. So let's jump in to the shell and tube heat exchangers. Yeah, why do we make new models? So one point was to simulate more accurate filling charges, which is possible thanks to the void fraction model. And the new models also have optional multiple tube side passes. So this is, for example, an evaporator model where the flow from the refrigerant side is going from the bottom to the top. We have one finite volume in this model and a filling charge. And this filling level is also depending on the void fraction, which is occurring below the filling level. So here we typically have something like nuclide boiling and gas bubbles. And this also affects how much mass is in such a heat exchanger. Above the filling level in the evaporator, we have saturated vapor. And in the condenser model, it's the other way around. We have a vapor-dominated phase with droplets and a saturated liquid phase below the filling level. And these models are also robust and accurate in a closed system. Okay, next I'm looking into the compressor model with vapor injection. So yeah, typically these models have a third port, and yeah, they enable the analysis of improved efficiencies in refrigeration systems. So let's go step by step from the suction inlet on the left side in a pH diagram, which is shown here on the right. So our loss-based or physics-based models typically have a suction side pressure drop, and then we have a suction volume here on the left side, an isentropic compression. So then we are here at the point 3 before the injection, and the pressure at the outside of the injection port is a little bit higher than inside. So therefore the flow goes into the compressor at the injection port, and we have another sort of second stage of isentropic compression, a high pressure volume, and a discharge pressure drop. So we are ending here at position 6. From the inlet 1 to 6, we have different losses. And typically we have a mechanical port for the shaft power and a replaceable friction model. And these losses can be brought into the high pressure or suction volume. And it's possible to model the leakage here in between. And we recommend to parameterize these models with a model fitter and fit them against measurement data. Now let's have a look at the new splitter models. So we had models in TIL under heat exchangers and different kinds of models, but now we have these unifying splitter models for all fluid types. You place them before your parallel fluid passes, and at the end you are merging the passes with the volume typically. So you have two different options. The one is to calculate the momentum balance correctly. So the mass flow distribution is hydraulic, correct, calculated, and therefore you need mass flow dependent pressure drop models in each pass and each model here inside. The other way is to say, okay, I don't want to calculate this with the correct hydraulic splitting, and I know the mass flow splitting. So for design purposes or something like that, it's maybe more easy and robust to define directly which are the splitting factors with a fixed parameter set or via input. Therefore, you just need to switch this flag to false. In this case, your inlet pressures may differ and you get additional pressure drops or pressure differences here in the splitter. And these splitters can be used also for liquids and VLE fluids. Now I'm coming to the improvements to the TILMedia calculation routines. So here we have improvement of the spline models. So the B-cubic spline interpolated VLE fluid mediums had some inaccuracies around the critical point, which we improved. And we also updated the external library data from RefProp, which are coming from the National Institute of Standards and Technology. And there are a few new models or properties, and there are some changes in some pure fluids and also a lot of mixtures, which are listed here below. I don't want to go into much details. These lists are also available in the release notes with a little bit more information. And finally, I want to explain a little bit about the new TIL example to showing how a data center cooling can be modeled with our software. Here you see these modern liquid-cooled CPU racks in the middle of the system, which are in a controlled overall thermal systems. So we have this inner cycle here with a pump and different valves to cool down the CPUs. Then we have another cycle here to bring the waste heat maybe to a local heating system to recover a part of the wasted heat. And we have also the possibility to bring the heat to rooftop units here and going back to the pump and closing the loop. And a part of the heat is going also into the room, to the air of the data cooling center. And therefore, we have here a little air conditioning system. This air conditioning system can be looked at with a state chart, for example, with a pressure and specific enthalpy diagram in DAVE, as it is shown here. And yeah, we are controlling different things. For example, we can control the return temperature with the pump speed here, or the mass flow rate of the pump. And we are controlling each temperature of the CPU racks with the valve opening. And we have in the example a little heat load ramp at the 5th CPU rack to have a little dynamic and difference between these 5 racks. Then we control the air temperature in the room with the compressor speed of the air conditioning system, and we control the subcooling with the TXV or with the valve area. Yeah, then it's maybe interesting to have a look into the heat exchanger and their temperature profiles. So for design purposes, it's always good to have a look at the temperature differences in these heat exchangers. Therefore, I added here the plot for the condenser and for the evaporator of the primary temperature and the secondary, and as well the wall in between. Yeah, due to time constraints, I'm not showing some add-on improvements or new models like the electrolyzer models in the add-on of hydrogen energy systems. But yeah, we feel free to contact us or ask any questions. So I'm at the end of my presentation and giving back to Christian. Thank you.
Thank you very much. I think we can start with the next presentation right away.
Yes, thanks, Christian. Just let me share my screen. Yes, so hello from my side. My name is Andreas Fachmin. I'm one of the developers of the TIL Add-On Battery. So I'm going to talk about this new TIL Add-On Battery today. We call it new add-on because there's obviously an old one. This old one had its roots, I think, in 2012 or 2013 when Ingo and I did our first steps in battery simulation in Modelica. But of course, a lot has changed in technology of batteries, also how users or what users want to simulate, users want to parameterize components and so on. So we opted here for a fresh start. What's inside the TIL Add-On Battery, or what can you use it for? So today I'm going to talk about 3 use cases. The first one targets TIL users who are working with thermal management systems, heat recovery systems, that want to integrate heat from batteries into their systems. The second one goes more into the details of batteries, into battery thermal management systems. The third one is focused on battery safety. So let's directly start with the first one, integration into thermal management systems or other systems. So here on the screen, you can see a typical TIL cycle, ASU2 refrigeration cycle, and in the middle part of the slide, you see this battery stack model. So this battery stack model is a fast model, a discretizable model, easy to parameterize, and it can be connected to other TIL models via a cooling plate. Here you can see a liquid cooling plate. You could also use a refrigerant cooling plate or just a connection via heat ports. Yeah, so as I said, it's easy to parameterize. You don't need too much to make it work. I think that's why also the application is really integration into other cycles like automotive cycles, other mobile thermal systems, stationary energy storage systems, and so on. Yeah, and I'd say let's move directly to Daimler and have a look at the parameterization. Yeah, so here you can see the same system I just talked about. Let's just double click on the stack model. So you can see on the top part here, we define how many electrical cells we want to simulate. So here I went for 120, which is more like a whole battery system. So in this case, this battery stack model represents a whole system. You can define the electrical connections and of course also the cell itself. So like here, capacity or cell geometry, solid and so on. And below that, you see this discretization part where you can see that there are 3 different parameters for discretization: north, south, west, east, and top, bottom, meaning that we discretize in 3D here. So I opted for 10 times 3, so 30 discretization elements. Having a look at the electrical part, you can choose the equivalent circuit model. So here I just chose a resistance model, and you can choose how to parameterize this: constant resistances, constant capacities, or table-based ones, equation-based ones. Yeah, and this is more or less all you need to set up this model. We can also have a look at the cooling plate. Also here, you just define your geometry, define the discretization, what the fluid or flow direction is. You can choose from heat transfer models, pressure drop models, and you can also include a gap filler. So this part or this component between battery stack and cooling plate. Yeah, that's it for the first use case, and like to go on with the second one directly. So battery thermal management systems. So as I said, it's more to have a more detailed look into the battery itself and to see what's a good way to cool them, to heat them, or whatever you need. So in this example here, we do see a stack consisting of 12 cells. Underneath, there's this liquid cooling plate with this kind of S-shaped flow. And on the top of the stack, you see these cell connectors or stack connectors that also can get quite hot depending on current. So to model this, we also use the introduced stack model. And here we're using a little trick. We use 3 of these stack models to build one stack. So using this, we can really kind of build the stack quite flexible. Also, maybe if there's some intermediate layers between cells and so on, you can build it like this. And the result, for example, looks like this. Yeah. So this result looks more like a result from a 3D environment, and it's really not the top ceiling of what you can reach regarding discretization. So you can really discretize a lot higher than shown here, and really go into detail. And I think, so I would say a transient simulation of this kind of stack takes under 5 minutes. And also, of course, you can use different CPUs also on a laptop. So you can, so what this add-on is really great for is just comparing different topologies, liquid cooling, refrigeration cooling, topside cooling, downside cooling, sandwich cooling, and so on, different volume flows, temperatures, and so on. And then you can really use can do like 10 simulations in under 5 minutes. Of course, you can also do this in transient. We are regular doing transient simulations, have a look at state of charge, have a look at voltage, and so on. All right. So then I'd say we've already had a look into the stack model at the last use case. So I'm going to start with the third use case, which is a bit different. It targets for engineers who want to have a look at battery safety. So we talk of thermal runaway and thermal propagation. a thermal runaway, for those of you who don't know, means that one cell or one battery cell gets triggered, for example, by a high boundary temperature, by any kind of penetration, and then there's this so-called thermal runaway occurs, where there's an exothermic reaction and the battery gets quite hot, 800 degrees, 1000 degrees. And then thermal runaway, thermal propagation means that one cell infects the neighbor cell, which then also goes into thermal runaway. So one example here is this one consisting of 5 cell models. And this cell model is way more complex than the stack model we already introduced. It also, it also consists of an electrothermal model, but it also consists of reaction models. So you can represent normal behavior, but also abuse behavior. And also can do both in one simulation. So for example, you can simulate the thermal propagation in this kind of experiment setup we see here. Maybe let's have a look at a result. We did a kind of validation here where you can see each color line is one cell. So the red cell, the first one, gets triggered, gets quite hot, goes into thermal runaway, has this exothermic reaction, and then one color after each other, one cell after each other, also goes into thermal runaway. So with these kind of models, you can analyze different cells, you can analyze intermediate layers, materials between the cells, you can analyze different cooling topologies, and of course also everything all together. So as said, this is based on a complex cell model. This complex cell model is also a discretized model with the electrothermal model, the reaction models. There's also a discretized housing depending on pouch cell, prismatic cell. There's a headspace. You can include venting holes. You can include tabs or terminals on different sites. And for the reaction models, one way of looking at them or analyzing them is, for example, this diagram from a so-called DSC experiment, where you see the heat flow over temperature. I would also like to show you this model briefly. Just having a look at the cell model here. So of course also here you can choose solids, you can choose geometry. The geometry can be quite complex here. You can choose the 3D discretization. Also, you can choose the electrical model, capacity, and so on. Here, we don't calculate the electrical model, just make simulation of thermal runaway and propagation faster if we just switch this off. And then under thermal runaway, you can choose thermal runaway models, choose the mass that's lost during thermal runaway. And you can choose if you want to calculate the thermal runaway model for the whole cell or just for each discretization element. I think I just reached my speaking time, so switching back to my slides. This was my last slide. I think especially regarding thermal runaway and so on, I just touched the surface of the modeling of this multiphysics and so on. If you have any questions, please reach out to me or also to my colleague Finn. Now back to you, Christian.
Thank you very much. And I would like to hand over to Mario.
Thanks, Christian. I will go share my screen and show you all the new stuff in Dave 2026.1 and 0.2. Dave is also our visualization environment, and for complex systems, thermal systems, whenever it gets complicated, Dave's at your side. My name is Mario Schlickhoff, and I'm the product manager of Dave. And of course, I'm in style, and this slide is in Dave already, and I would like to just connect to Andreas' presentation and show how a simulation of the battery thermal system might look like in Dave, and where Dave could enhance what you're seeing, what you're getting from the MoBA script Andreas just showed, all these this fuzzy 3D view with all the discretization cells is static, so you just get one point in time where you can actually analyze it. And we got these slices down here. The red slice is the second one from the top in this 3D view, and the blue one is the second one from the bottom. And we have this these three substacks. You can see them, you can distinguish them because the cooling system is meandering under the cells. And that's what we are going to have a look at. I've got a graph showing the maximum temperature and the minimum temperature in each of the substacks. This is the red, orange, and yellow line. And the blue, you can see the electrical current, which is drawn from the battery, and which leads to a temperature rise, of course. So whenever we draw a current, the temperature goes up, and in these little pauses, temperature has some time to recover. And if I just let the simulation run, or the visuals run, we can see how in this XY vector line plot, how the coolant actually enters the cooling channels and how all the different channels are cooled down and the battery itself is heating up. In red up here, we can see the current simulation in this overall view. And I will just speed it up a little bit. And we can see how the simulation gets from the initial state to a running state. And if I slide through the time, we can see that the temperature in the in red, it's the temperature of the bottom of the cell, and blue is the liquid temperature. We can see the cell temperature rise, and we can see a spread in the liquid temperature, which always enters with 20 degrees Celsius and leaves with a higher temperature once the battery cells are higher. So having some plots made with Matplotlib is fine, but Dave can give you more insight, especially in transient simulations. So what's new in Dave 2021.1 and 2? Well, first of all, I've got a enlarged view of this thermal battery overview plot. And the first feature I would like to show you is that in some graphs, and people always say sometimes they have a lot of plots in the Dave, a lot of lines in the Dave plots, and it's hard to distinguish what line is what. For example, in this case, I deliberately chose similar colors, so it might be not so easy to actually have a look at one of these lines. But now you can, if you just select one of these lines down here, you can highlight it, and all the other lines are just black or grayed out. And one you actually want to highlight is still visible. So especially in a very complex situation, or where you have a lot of overlapping, that's a feature which might come in handy to actually separate your data. The second feature is that people wanted to have more control of how plots look like. And you can already in previous versions change the font and the size of the axis labels, but you couldn't change any of these tick labels, the axis itself, or the background grid. But now you can. And I've got one version where I just changed a lot of stuff just to show what you can do. You can do dash lines for the grid. You can have a red axis. You can have red tick labels. On the blue side, on the right side, I've always also added these in blue. The time variable is black and enlarged. And I went ham with the legend and just added some background just to show you that you can do a lot of stuff, and you can just customize it to the way you might want to have your visuals. You can also if you want to, add a background image. Yep. Yeah, here we go. You can change the background. There's a lot of feature or a lot of settings you can control here, but you can also add an image. And I just added an image of the battery. Does it make sense? Probably not in this case, but just to show you, you can do it. Maybe sometimes it's really nice to have a feature representing image in the background, or you can use it, for example, for a map. If you want to have a map of efficiency, and you have and you did create the map in some external software, you can import it as a background image and do an XY point instrument in Dave, and then you have your actual efficiency point in this map image going along. A third feature is that we changed the way you can alter the x-axis. So usually in Dave, it's always the time, but you can change it. Before, it used to be you would have to add a variable and then leave the configuration, right-click on the diagram and change the X variable. Now it's available just in the normal config menu. And I can go from time, for example, to current, which also does not make sense in this case, but it's very easy to just change the variable this way. Okay, next up is automatic labels. If I need to leave full screen mode, if you go to preferences, under instruments, general, you have y-axis label. And if you check this checkbox, axis label from variable, Dave will automatically add axis labels depending on the variable you add to the graph. And now I added 2, which is not what I wanted to do. Okay, go. That's what I want to do. So if I add this variable to this graph, you can see that we have an automatic label showing the name and also the unit. And if I add another one, you see that Dave automatically drops the name because the names are different, but the unit is still the same. It still shows Kelvin. And if I add another variable that has a different unit, then Dave removes the label because there's no common information. So for quick overviews, that's a very nice feature. If you want to just plug in some data to some graphs, for example, just drag it here, and then Dave might to create automatic labels. So another feature is the psychrometric chart. Here in Europe, we use the Mollier diagram, which is just one variant of a moist air diagram. I've got a comfort zone for somewhere in here. And if you're from America, which some of y'all might be, because this is the English webinar, then you might be more familiar with the carrier diagram. And as always in Dave, where you can just change one state chart to another type. You can also now change the Mollier chart to the psychrometric chart or carrier diagram. If I do that, it gets rendered, and it's basically just a rotated and flipped version. So if you need psychrometric charts, you can now use them in Dave, and you can also just switch from one to another if you need to. And the last thing I want to show is, I've got another Dave here. We added some new examples. A lot of people do not know that we have some nice examples right in Dave. You can just open them with this example finder. And under state control, I have added 2 new examples, an H2 filling station, showing how a H2 car might be filled up with different pressure levels, and you can just use the slider, or the Volkswagen R744 heat pump they're using in their ID models. This is an example using state controls with 2 lines for the coolant and the refrigerant line, and you can just switch different cases and see how Volkswagen does their thermal management. And this example also includes one new feature, which is links. We wanted to disclose where we get all this data from, and Volkswagen themselves showed it. And if you see this link icon in Dave and you just click it, and you click it correctly and not next to it, then a link will open. It can be a link to some page in Dave, or it can be a link, like in this case, to some page in the internet. And with that, I'm done, and giving back to Christian.
Thank you very much. And I will hand over to Philip.
So, good evening from my side. My name is Philip Ebeling, and I would like to start with a short personal note. I'm one of the developers behind MoBA, but I'm also an active user, and that's very important for me because my main motivation has never been the automation for its own sake. My motivation is the efficiency in daily engineering work, so that we can spend more time on understanding results and less time on producing them. I enjoy looking on real engineering workflows to identify where the effort is wasted and to find simple, pragmatic ways to unlock the potential. That mindset drives the things I will show you today. So for those of you who don't know the MoBA Automation, MoBA is a platform that turns engineering workflows into structured, explainable, and scalable processes. And that's without hiding what actually happens. That means we have explainable automation so that you always understand what the system does. We provide scalable collaboration across teams. And of course, we bring into our deep domain knowledge in thermodynamics, simulations, and measurement. So, the two topics I will focus on today did not come from a roadmap, but from a very intense discussion with a project partner. So we closely analyzed how they actually work. What we saw was a recurring pattern. So engineers develop and validate system models, for example, in TIL, continuously in Daimler. And at the same time, they run daily large simulation studies to check the target criteria. So the model logic and the study logic are linked, but they are maintained very differently. So on the one hand, the simulation studies were well documented in MoBA, for example, but in the modeling environment, the similar assumptions and the boundary conditions, they had to be maintained manually. And this created friction. And that friction is exactly where our first topic starts. So the first topic is master cases. So we looked on how our partner actually worked, and we noticed that the boundary condition and the common assumptions were usually well maintained in MoBA workflows, and that's exactly where you want them in a study context. And at the same time, those very same boundary conditions had to be transferred manually in the modeling environment, and that meant duplication. And more importantly, there was no fast or reliable way to select and reuse the sets of boundary conditions in the model. So what was missing was not the structure, but a shared concept between the workflow on the one side and the model on the one side. And this is exactly the gap the master cases addresses. So the master case is a formal container for simulation boundary conditions that are already defined in the MoBA workflows. But the key difference is that they are explicitly reusable. So the master case provides the defaults, and they never override individual study definitions. And with the master case file, we also created an interface to make these boundary conditions available in the modeling environment, for example, in Daimler. But I won't go into the detail today. So this concept is also relevant in team setups. So the engineers run their own studies, but the boundary conditions are maintained centrally and consistently. So that reduces misunderstandings and errors. So I want to go directly to MoBA to show you how this is implemented. So for my simulation study, I use the ready-to-use workflow Daimler study here. And I instantiated this workflow here. And when I open the input interface of the workflow, then we see here the parameter file path we used so far to define the simulation studies. So what is new is a new input, which is called master parameter file. And when I open this master parameter file, then we see here a simplified table of boundary conditions. So we have only, or in this example, I only used two variables. So each line represents one boundary condition or one simulation case. So how can I use this case, which actually can be, or how can I use this parameter file? So when I go to the simulation study file, then I have to simply link the master case here in the master case file. So to use a corresponding boundary condition, I only have to fill in here the master case name. So and actually the set of boundary condition is filled up with the defaults from the boundary condition here. Of course, in the master parameter file, you can also define values which should be checked for steady state in the end, and other limits which have to be fulfilled after the simulation. And you can also define output variables which have to be considered in the automatically generated DAVE configuration or in the sample in the summary file. So when I perform the simulation and I go to the value viewer tab, so here we see the results, result files of the simulated tab, and I open the summary file. Then we see here that in the study cases, the normal or the defined case was filled up with the defaults from the master parameter file. So now the workflows are structured and more clearly, but then another issue become very visible. So the reality mostly isn't perfect. So simulations fail, the models change, the tools have bugs, and sometimes the results are generated in Daimler directly and they wanted to be integrated in the workflow. So and we ask the question, how can we address this in our workflow? So let's go back to MoBA. We implemented another input, which is called handling existing result, and we have there three options. The first option is always run the simulation, and the second and the third option deals how the simulator workflow deals with when it's restarted. So if the simulation files are available or they are already in the workflow, they will skip the simulation. So I can, if I select this option, I always can restart the whole workflow, and if files are existing, they will be skipped. If I have simulations from another workflow or manually simulated files, then I can integrate them in the post-processing just by providing here a directory, which is at the input existing results directory. So the only thing I have to adjust is to go into the parameter file path here. I open it here. So, and I have to address the simulation cases I want to integrate here in the study cases tab. So I have to have a corresponding case name for the file. So so the intention here was to integrate these existing results in the total study. And when I go back to MoBA and also have a look at the results here, then I see in total results that all results have been evaluated. So that's a possibility to integrate or to use the post-processing mode only for simulation. So both features follow the same principle. We try to support the way engineers already work. So was it from my side. And yeah, we would be very happy to engage if you're willing to share your workflow with us.
Okay, do we have questions? You can write in the chat. You can try to answer them. Okay, while you're thinking about asking questions, I can ask a question. Ingo, could you say something about the tubing configuration in the shell and tube? Is it possible to implement different tubing configurations? Volume. I mean, the volume computation is always a bit tricky in these shell and tubes. Can you say something about that?
I think you are focusing on the liquid side. So yeah, typically we have the refrigerant in the shell and the liquid, incompressible liquid in the tubes, and the tubes can now have multiple passes. So we have one inlet header with a heat capacity around, which is just giving the metal of the inlet volume, and then we have the pass and the discretization along the flow, and then a redirecting header in between to the next pass. And yeah, you can give any numbers of multiple passes and discretization cell elements as you like. Yeah. Typically we discretize heat exchangers with around 10 cells, but it depends on the temperature differences and yeah, the boundary conditions you want to simulate.
And the filling level computation?
Yeah, the filling level in the shell is initialized. So we have an initial filling level. So this is calculating the refrigerant mass, which is in the system at time 0 and also around the total simulation time. And the filling level can change, and it can also be controlled in the system, for example, with a valve inlet. And it is affected how much void fraction I have, for example, in the evaporator of gas bubbles or vapor, due to maybe nucleate boiling or something like that in the shell. Therefore, the filling level can increase or decrease, and also about the incoming refrigerant flow and outgoing refrigerant flow.
Okay. Any further questions?
But otherwise, you can also contact us. We have support email addresses or personal email addresses, and can be found on our web pages. And we've shown on the slides.
Yes. So please contact us if you have any needs of course, also feedback. We need your feedback to improve our software. If you want to provide feedback, we will be glad to receive it and to address it. Okay, so I will close the session. Thank you very much.
Thank you for joining the webinar.
Thank you.
Good day, good afternoon, wherever you are.